Okay. Yeah, so I got called for this 9 o'clock last night, and fortunately, retired or semi-retired guys who have lots of old slides are good targets for such things. Okay, so here's my usual history slide. Again, this is all pretty standard stuff. If you're watching this on video, you want to go look and get the actual slides. These were not designed to show up on TV screens. Sorry. Okay, right. So basically, I spent a bunch of time at Bell Labs. This is my license plate here in California. Right. Came out here. Bell system was breaking up. I saw the light, and bad times ahead. Was it? Pardon?
Rats leaving the sink.
No. Just, it was time to move. Okay, came out here, was at Convergent Technologies, got recruited by Hennessy and Company to go over to MIPS, did a bunch of stuff there, formed Spec, been in hot chips for a long time. We got acquired by Silicon Graphics, so I was doing computer architecture and chip things and software and things. And actually about 1994 started using the big data term, and I'll explain how that got started and where it fit and all that sort of thing. I actually got it to be an SGI marketing term, and I'll show you some examples. And these days, I'm sort of half retired. I still do some consulting, but I do advisory stuff. And I'm a trustee at the Computer History Museum, which is useful because I can scarf up slides and things. And then the rest of the time, I mess around. Okay. All right, so I'd sort of forgotten about this, but I got this call from a writer for the New York Times who's been backtracking where big data came from. And he says, so I've been looking for this, and it sounds like you might have had something to do with this, right? And I said, well, yeah, okay, right. So I said, it's not like I invented anything special. It's so simple, big deal, okay, right? But what I did do is spend a lot of time popularizing it within the high-performance community and some other places, right? And it was this sort of simplest thing that I could think of for describing data pushing and analysis that was on the edge of what was practical, right? We sort of already had big graphics and big compute, but some of the problems are really big data, and neither are the other two, right? Okay, so anyway, that's sort of where it came from. That's where the article is, and if you look at the Wikipedia talk page on big data, I sort of added some detail in there. Okay, now people would ask, has my definition of big data changed? I'll talk about that. I'll go through some of the history, talk about a little bit how we got here and where I think we are now, and a little bit of where I think things might go. And we have plenty of time for Q&A. So my definition hasn't really changed. I always thought big data was, hey, well, if it's kind of on the edge of what you can do, I'll call it big data. And that's a moving target, right? It could be on the edge for a couple reasons, but typically, if it gets a lot bigger than the main memory capacity, or it really stresses I/O performance, or it's got really difficult real-time issues with the data and streams of data coming, that's where you get big data from. Or if it's complex and difficult, messy kinds of different data, that rapidly turns a moderate volume of data into maybe a big data problem, particularly if you can't sort of stream it, if you have to do random access all over the place. But it's also, again, a moving target at any time. Usually there's something that's trivial. Anybody can do it. Then I'd say easy. You got some disks and you've got something that's sort of a standard configuration, and it can do the job with pretty standard software. And then you get big, where it's, you need a lot of work, and sometimes you got to roll your own, and some serious people got to think about what they're doing. And then impossible is, I don't care if you're the NSA, well, whoever you are, okay, right? With infinite piles of money, it's still just, it just doesn't make sense, right? And then this is a moving problem, of course. Now, I see plenty of old timers here. I bet, how many people here have used key punches? Yeah, well, this is not exactly a typical audience. Okay, right. You may remember we had a 360-67 at Penn State that had a meg of main memory and 8 meg of large core storage. Okay, luxury. Yeah, I know. Well, I go back further than that, but I know. Hey, come on. I programmed an Olivetti program of 101 with 128 locations. Okay, right. So come on, give me a break, right? Okay, so obviously all this stuff fits in cache memory on a laptop these days. Big whoops. Okay, right? But I observe, big data has really been around for a long time. I like to start back with these guys. So here's a Hollerith machine for the 1890 census, right? Because the problem was the government put out for bids because population was growing and they couldn't complete the census processing before the next one came. Okay, right? Yeah. Okay, so what this ended up causing was, it ended up they could do it in a couple years, and of course Hollerith, he's now got these machines that are come off lease. How's he get revenue from this? And of course there's the punch card industry and all that. Yeah, it's a shaver and blade stage. Okay. Now, what's funny with this is a few years ago, I took a gang of first-term Stanford freshmen in the accelerated computer science program around. Well, you know what these kids are like. They're 18. They've hacked C++ for years. They built their own Linux machines. You know the type. Okay, right? But they'd never seen a key punch, right? Okay. And they looked at punch cards and they said, what did you do this? Oh, this is how we wrote code. No, nobody could write code that way. How could, they were muttering, nothing. How could they do this, right? Okay, and I said, wait till you see paper tape.
Is there one of these at the museum?
Yeah, there is. Oh, now how many people have been to the Computer History Museum? Okay, well, shame on you. You need to go. All right.
Explain your ignorance.
There was a person there that's not shown.
I want to see you operate the Iliad.
No, we did not restore that. We have some old machines running, but not that one. Okay, well then, we got this stuff, say 1950, key punches, sorters, plug boards. This was code, right? Code for the time. And this is what you did. You set up all this stuff and plugged in the right things. And I actually used some of this stuff because I knew how to use IEB print punch utility to sequence card decks, okay, right? So that if you drop them, you could sort them and put them back, right? Okay, great fun. Then, big data. Hey, about this time, 1960s, big mainframe was one of these. Of course, 16 megabytes was the memory limit, right, for a terrible mistake, all right? Do people know why that happened? Why did they only use 24 instead of 32 bits?
Top byte is a great place to put a flag.
No, I did a lot, okay, right, but that wasn't the reason. The reason was that the 36030, which was the big model, was a byte at a time machine, and it saved a clock cycle to do that. And they decided to make that addressing limit for that machine, okay? Probably a mistake. Anyway, you could get a couple 2311 disk drives, each with 7 megabytes, but 2314s were 28 megabytes. Good stuff, okay? All right, so, 10 28 megabyte drives was a fairly substantive kind of machine at that point, right? Now, we actually had a thing called a noodle snatcher, which had 400 meg of random access storage. And this had strips hanging down, and you would rotate this drum, and things would come and spread the strips apart and snatch one up and put it on a drum and then move back and forth and read it. Sometimes when they put it back, it would have relaxed and it would jam them in there, right? So, but anyway, it was a strange machine, but it worked. Now, important thing right about then is when virtual machines got going, right? 36067, CP67, CMS, kind of a bootleg project up at IBM Cambridge. But that's important, right? Because later virtual machines come back and they're pretty important to what's going on now. Now, what's interesting is, of course, at the time, most people couldn't afford big mainframes, so there were service bureaus. Okay? Kind of reminiscent of the cloud, okay, right? But they just weren't the cloud, right? Okay, where were the wars? One of the things that goes on in this time is at each period of the history, there are stack wars between different stacks as to which stacks of hardware, software are what people want to use. And here, the stack wars were between big vendors who had a complete bottom-up stack of their hardware, their compilers, their operating systems, their utilities, and then maybe there were some applications on top. Okay. All right, in the 70s, the IBM 370 actually got virtual memory. That was kind of a nice thing, right? Still, the machines weren't that big. And certainly mini computers were not big data yet, but they were starting to get rolling. When I arrived at Bell Labs, I got my group got the second PDP-1145. It had 248 KB of memory, okay? And we supported 16 users on that, which was fairly exciting. Right? We got these huge PDP-1170s. We got 48 users on that, if you can imagine. And disks were starting to get bigger. And what was going on right then was clustering to mini computers to compete with mainframes at lower cost. Okay, right? Let's see. Well, microprocessor, and of course, here's one. Yeah, it's Ritchie and Thompson, at an early Unix machine. Microprocessors were toys. Late in that decade, but anybody with any sense knew that's where the action was going to be, right? You could see them coming, workstations got going, but the mini computer mainframe guys, yeah, forget that, right? The stack wars here were often in algorithmic languages and sometimes operating systems. Right? So there were wars over whether C would ever be any good, or was it PO1 is where the future was, or Ada, or whatever you like. Don't laugh. APL. Well, hey, no, APL was before that, right? And I like to use APL, but it was a write-only language, so it was kind of hard. Okay, Bell Labs. So when I was first, well, I don't know if people remember what that was like. The Bell system was 1 million+ people. Bell Labs itself was 25,000 people, which was pretty amazing. The way I would summarize this is monopoly money is good. Okay, right? You can do things, right? The first half of that time, I was working on this thing called the Programmers Workbench, which is the version of Unix that took it out of the individual lab to be more the utility thing. We did security things and shell programming and a lot of other stuff. I used to give a talk, ironically, called Small is Beautiful and Other Thoughts on Programming Languages, which is funny to find in a big data talk, but still, it's okay, right? Unfortunately, if you look at the description, I did not coin the term agile software, right? I should have. Big data. Well, Bell Labs did big data then, right? We had a group in Murray Hill Building 5 who got all of the call records. The ones that the NSA isn't supposed to get all of, okay, these days, right? And they analyzed them to death up there, right? And now they had a whole lot of rules around this about who could look at this stuff. But they worried a lot about this, both for network design, but also for marketing reasons. I mean, after all, Bell System would charge people for 10-cent phone calls, and give you a bill with all that stuff. So they had to have all this stuff, okay? The second half. Pardon?
It cost them $1 to send you a bill for 10 cents.
No, it wasn't that big. But they'd send you a bill that would have itemized things to 10 cents. Okay, so all right. Anyway, then later I worked on a thing called the Loop Maintenance Operations System. And this was an IBM mainframe with triplexed mini computers for reliability. It's a distributed data system designed in the late 70s. And the idea was the mainframe ran the big sort of relatively static data about the phone system, and the mini computers ran the more active calls, okay, right? If you had trouble with your phone, the person you talked to was hooked to one of these things, and that had to be up, right? Or the public utility commissions would beat on you, right? And they would keep track of lots of details, right? I mean, this classic big data problem, they would keep track of things like, what was the failure that caused this trouble report? Was it a squirrel bite? Was it man-made problem? Was it gunshot? Okay, right? Gunshot was only a problem in the South and some of the West and Maine. Okay, all right? Okay, and they knew stuff like this, okay? Yeah. Anyway, okay, so I was doing a back-end data mining system, and there was an offshoot that was an expert system, the first one done there. The transaction stuff went through this thing and ended up in Oracle, okay, as the path there, right? So this is a pretty interesting gang. This was a sort of aggressive development group that always used new technology but could still get products out. My director ended up later as the CTO for Bell Labs, and the guy he brought in to replace him was later the Bell Labs president. So this is a fairly serious group. Now, yeah.
Include basic Bayesian inference?
Pardon?
Was there Bayesian inference in your?
No, I wouldn't dignify it with that. Okay, I mean there was. We don't want to go. It's going to go too far afield. Okay, right? But I had some cognitive. I had a group that had cognitive psychologists in it. Okay, right? So one of whom was really interested in expert systems and from the time, and it went off in that direction. Because the problem was you could train cable analyzers to use the reports from this thing to figure out what was going on. And when they got to learn it really well, then they'd get moved to something else. And you'd start over, okay, all right? And that was a pain. So we decided we should automate it. Well, you know what? I get really amused with the cloud. I'd swear every presentation I ever saw in Bell Labs had a cloud in the middle, all right? Now, the cloud was, of course, some version of the telephone system or a data system built by Bell Labs or something like that. But the cloud, you had to have a cloud, you know? I mean, just there was always clouds, right? Now, they were actually trying to build a thing that went under different names with processing in a network and dumb terminals at the edge. Okay, and they started this about 1975. I think they spent maybe close to $1 billion. It was too early to build that. You just really couldn't do what you needed to do. And by the time they finally got something to work, of course, dumb terminals were kind of not what people were doing anymore. Too bad, right? Too early. But clouds were there. All right, how about 1980s? Teradata. People remember Teradata? Okay, all right, there's a classic big data company, although they only started to call themselves that in 2010, all right? And they had been building big systems for a long time, and they would make very unusual systems to do data mining and data warehousing, whatever you wanted to call it, right? Okay, and they went through some interesting corporate things because they got bought by NCR and then to AT&T and then back and then spun out, you know, sort of a tough time. Okay, important thing, RAID disks got going over at UC Berkeley across the bay with Dave Patterson and company. That was obviously pretty important because it was getting harder to make big disks cost effective, and making cheap little disks work well, that was important. So, again, maybe not called big data yet, but the signs were there. The stack wars about that time were networks. You know, there were a lot of fights between DECnet and TCP/IP and other combinations. There were database management wars. Remember, we had all of these things fighting it out right around here. I seem to recall things like billboard wars on 101, right, when they would fight with each other, right? Then there were Unix stack version wars, typically by vendor, but then there were camps of vendors all agreeing or not agreeing. That was jolly, right? Then there were the distribution wars. Is the action in workstations or client server or PCs or thin clients or different combinations, right? We went through all that stuff, right? And then we got into the microprocessor wars, where I spent a bunch of years. That was a lot of fun too. Now what's pretty clear is, you know, by the late 80s, it was pretty clear that you should build bigger systems out of more commodity microprocessors, right? The economics were just too good. You could not go build one-off large designs. Interesting, the automobile business seems to be going through this right now. Sort of, when you look at electric vehicles and hybrids, sometimes you can use the same components in different structures, and it's a lot easier than doing it from scratch. So in 1988, we started design on the MIPS R4000, which finally appeared in 1991. And that got to be interesting. I'll talk about that. Stack wars also, we had Windows systems. People had different Windows systems and graphics interfaces, and we got to fight over that stuff. But yeah, now most of these stack wars sort of settled out, and that's going to be part of what I'm going to get to later. Okay, now come the 1990s. Browser wars, the World Wide Web, all this stuff really got it going. One SGI machine shipped in early 1992. As far as I know, it was the first production thing with a 64-bit chip in it. The first product out the door was still running a 32-bit OS, right? But what we knew was we had to get the hardware base converted over, and then we could shift to a 64-bit OS, right? That's a tricky conversion. Later in the year, the DEC Alpha systems came out with 64-bit chips and 64-bit only everything, right? And some people criticize them for that. I probably would have done the same thing. If you're starting from scratch with a brand new chip architecture, you might as well, you know, keep it simple. Okay. Now, as it happened, this was wonderful because unlike all the rest of us who already had a 32-bit architecture and kept that working, they only had 64-bit, so they paid a lot of money to software vendors to make their software 64-bit clean. So they did the rest of us a huge favor because they spent a lot of money to make this happen. Okay, so by 1994, SGI had big systems. We had 32, 36 processor systems running a full-bore 64-bit IRIX. We could support 64 or 32 users. We could go up to 16 gigabytes of memory about that time. We had a really great 64-bit file system, journaled. You could pull the plug on it and terrible things wouldn't happen. And this, by the way, later got contributed to Linux, right? And I'll talk about how that happened later. At that point, it was truly a really aggressive, wonderful file system. We finally got to the point then where customers could just recompile a Fortran program and use as much memory as they wanted, and life would be good, right? If it was at all portable. And again, fortunately, these guys had helped us make sure lots of software was just portable. But Fortran, the Fortran folks were all chomping at the bit because they knew they could just recompile, and they didn't really have a problem with pointers and stuff like that. They were in good shape. Now, I wrote about this. There's an article in ACMQ called Long Road to 64 Bits, Double, Double, Toil, and Trouble, because it was. And that showed up also later in CACM, because it was a lot harder than it needed to be. Right? I mean, this was a surprise to me because we knew in 1988 what's the most predictable technology trend in the business? It's the size of DRAM memories. There was a long period where the DRAMs just kept doubling, And, if you did the arithmetic, you could say, by 1994, a medium-sized server could easily have more than 4 gigabytes and still be in the same price range. And if we don't have some software ready about that time and the right chips, it's going to be messy. And those of us who've been through before the hacks to get around the inability to address all of memory, the things people used to go through in the old machines were real, for operating system guys, were pretty painful. We didn't want to do that again.
It's real painful to get users to upgrade.
It's always painful for that. Okay, now, I apologize for some of the fuzziness. This is from a video, right, that I did for another entity, and I had to sort of take screenshots and things. Okay, but this is what I was talking about. This is a talk I gave a lot of the times. This is sort of my vanilla talk for a general audience, right? And this is where I started using the big data. The idea was, okay, what do we do at SGI? People have a lot of data coming at them, or they want to create it, and they want to get insight from it. What do you need? Well, you need graphics, you need good fast chips, you need multiprocessors, digital media, you need good human interface, and you better have good I/O, right, to move all this stuff around, right? So that's when I sort of started using this, and I used to give talks like this saying, here's hardware, it keeps going up. Hey, another good thing is the amount of cost that you have for the amount of hardware. But unfortunately, us wetwares, we are still release 1 wetwares, and we're not likely to be upgraded anytime soon, right? And the idea being that software's got to fill in the gap between the good stuff and the not so good stuff. Okay, so SGI was known for apps, VisSim and design and research and analytical chemistry and oil and gas and fluid dynamics, especially, and animation for the movies and stuff. But the push here was we had all this great technology for pushing a lot of data around, right? And my argument was, look, we do big graphics and big compute. But some of our customers don't care about that. What they've got is just a lot of data. They don't do a lot of computation on each part of the data, but they've got to manage a lot of data. And we have these machines with high I/O rates because of the graphics. We have 64-bit everything, so we're not up against some limit. We're making scalable machines. There's all kinds of markets we should go for that are outside of SGI's normal thing. But certainly by 1996, big data was part of our marketing message. Okay. And, you know, at least some of this were in other application areas. They weren't just in the classical science kinds of things. And, you know, so that was a logical extension. I said publishing in quotes because publishing clearly at that time was including the web and all kinds of other things of digital media that weren't just making black and white images on paper. There were interesting new visualizations. You probably can't see this very well. These are interesting. It's a map of the U.S. where bars go up and down. You have a slider bar by a year, right? You would do things like showing the average income per person in a state. And if you did this, what was really nice is you could see things where some states suddenly changed relative to the other states around it, and just looking at a table didn't tell you that. So when you did that, you would see things like there's this period in the 50s where Kansas certainly leaps up relative to everybody else and it goes down, and South Dakota leaps up and goes down. Right? Everybody want to guess what that was? Minuteman missile bases being built. Okay, right? And the idea is that you needed to have smart software to make sense of big chunks of data that were floating around, okay, right? And if you could get the right visualization, that would help. Another one was a thing like a data helicopter where you'd see your file system out in the distance and the heights would be the size of files. And if you saw something interesting out there, you could fly out there and sort of look at it. Right? And I'm not going to show it, but you actually have probably seen this. How many people have seen Jurassic Park? Okay. Do you remember the scene in the control room where the velociraptors are coming for lunch and the humans would rather not attend? Okay. And the little girl sees the computer and says, oh, Unix system, I know this, right? And she sort of flies around through an image of the locks. Well, that's this, okay, right? That is not in the book, okay? The ILM guys saw this and thought it was cool, so they stuck that in, okay, right? It was sort of an in-joke. Okay, and I used to talk about, you know, this was sort of the architectural things of all the classic bandwidth latency things, noting money can buy bandwidth, but latency is forever, right? Because the speed of light is the speed of light, and you cannot bribe God, okay, right? And I had some things of, well, you know, so this is what we're getting, and this is where the ranges are of things, but unfortunately here are the bandwidths for humans, you know, and we're kind of low, you know, on this, and we're not likely to get re-engineered. And all that implied was, you know, if you've got a lot of data, you've got to push it around and do a lot of good graphics and things to figure out what's going on, because we're not that fast. I note, for instance, that historically, every time you change how long it takes to get an answer, the applications tend to change. Okay, right? So for instance, if you start off with something that runs, you know, a million seconds or so, you know, they run for a long time, you get the answers back. Long-running weather simulations or climate simulations are like this, right? Okay, when something gets to overnight, you now get things like electrical CAD logic sims, you know, that you want to run overnight and see the results when you come in the next day, right? Hey, if something goes here for an hour or so, that's not too bad. You'll run it while you're doing something else. By the time you get down to here, you'll run it and look at it. And when you get it down into here, it's something you can use like a mouse. Now, you know, if you have a mouse that only responds once a second, it's not good. It just, no one will do that, right? Okay. So, observation is things keep doing this, and then when they get down to here, then you worry about cost reducing them, all right? But clearly what goes on is some of the big data stuff has moved from being a really long time thing down to being something that's, you know, pretty good here. I mean, after all, how long does a Google search take? Right? I mean, it's down in this turf, right? And if a Google search was 100 seconds, it would probably not be used quite so much as it is. Okay, well, anyway, by 95, SGI, a chunk of it had gotten to all kinds of things. And again, there's banks in here. There's commercial things. They're running different databases. There's oil and gas like we'd been in, but there's financial folks, right? So there's a lot of things that no one would ever think of SGI doing. And they were typically big data apps. is what they were. They weren't huge, but they were big enough to be stressful, and they were using 64-bit stuff, and they were happy.
When did SCSI cables come along so you could get enough disks on machines?
That was about that time, yeah. I think they were SCSI about that. But yeah, I mean, all this was a moving thing. That's a whole different, there's a whole talk I used to do on that stuff. Actually did it right here for EE380.
SCSI came way before.
Well, SCSI was before, but then it kept coming down in cost, and it got into the bigger machines, right? Because it was too cheap.
Well, 16-bit. It was SCSI to start with.
Right?
It started off being a SCSI.
Yeah, it started being SCSI, yeah. Okay.
Some of the old parts of it.
Yeah. Okay, so anyway, there was a lot of stuff that you would call traditional big data companies today, but that was going on back then. Now, the issue was, of course, is it wasn't using small, cheap machines. These were still 100,000, couple 100,000, maybe $500,000 worth of machines. So this was not some random little startup doing it. Those kinds of folks I showed up here, were serious-sized companies that were doing this, right? But they were doing the same kind of stuff. Okay, so then here we were about 1996. These were examples of folks who were doing big data. And again, I got our marketing folks to be using the term, right? So for instance, red brick data, that was called data warehousing sometimes, or data mining, right? And these were business kinds of things, and these are what they were doing. And again, it's not what you'd think of when you think of Silicon Graphics, but it was actually a fair amount. These were some of the other examples. Banks. I used to go to Wall Street a bunch, right, and talk with them. And they had classic big data problems. They were not doing classic supercomputer stuff. They were doing big data stuff. This was an interesting one. Telcom New Zealand. There was a fault system, and there was a terabyte, big fight with terabyte. Of course, this was back when 1.6 terabytes of disk was a big disk farm, right? That, of course, was quite a while ago, right? That was a jolly fun thing. We replaced the Teradata at a much lower cost, and they paid for the machine in about a month, right? And it was classic big data marketing stuff, just like you'd see people doing today. Now, of course, it was still a $500,000 or $1 million kind of machine, but it's okay, they paid for it quick. And these, I guess, I probably can't talk about at the end. But yes, I used to visit Fort Meade. All right, now about 98, I was worried about the fact that storage was exploding pretty fast, and it wasn't clear software was keeping up for this, and I started giving this talk, Big Data and the Next Wave of Infrastress, that is stress on the infrastructure. And I did one at Unix, and there was actually one right here at Stanford for EE380 from this talk. Okay, this was about the same time. So now they were calling it strategic business analysis. So, the names keep changing. The underlying technologies changed some, and what people were trying to do was still the same stuff, but the labels kept changing, right? And these were the kinds of applications people saw interesting. Things like fraud detection are ones that are great because you have streams of data. There's sort of a real-time response kind of thing, all right? The kind of thing that, that causes Visa to call you up 30 seconds after you use a credit card in an odd place and go, yeah, is this okay? Right, okay, well, it matters, right? Okay, right? And that's nice, high velocity data, a lot of data, and it turns out to be good application. And we sold to a lot of those. And here were the kind of customers there. Again, what you see is just lots of commercial customers of one kind or another. So this is what I say, it was not what you expect, but what was going on. We'll skip that. Okay, so how about today? Well, let's see what's happened recently. Beowulf, technical PC clusters, you remember that got going? That wasn't really big data exactly. It was more how do you get cheap compute cycles at first. It was kind of held back by the fact it took so long to get 64-bit x86 chips. Right? This to me was, I understand how the market, that wasn't the focus of the market, but it's, in some sense for the computing industry, it's too bad it took so long, right? Because the handwriting was on the wall a lot earlier than that. Virtual machines, VMware and various others, right? After all, IBM had been doing VM for a long time. Virtual machines really started to come back in. you've got companies like Google with huge infrastructures and thinking hard about distributed algorithms. So now you see MapReduce, Hadoop, all this stuff. This, to me, looking at it from outside, this sort of did what for the relevant apps, what the parallel programming software did in the 90s for technical apps. Because in the early 90s, we had all these multiprocessors at SGI, but they were not easy to program. Right? Okay. You had to work at it, and the tools kept getting better. You didn't have to put as many directives in. You had auto-parallelizing compilers. You had cache blocking compilers. You didn't have to do all that stuff by hand, and more mortals could do it. Right? And I think in some sense what this did was, it's sort of just as the World Wide Web made the internet more accessible for doing applications compared to the old programming you had to do for distributed systems, this kind of did it for the database kinds of problems. Now, things like Amazon Web Services sure looks to me like, boy, they remind me of the 70s service bureaus. I mean, you know, it's kind of, hey, I don't want to have the machine and stuff myself. I'll buy the service from somebody else because they're good at it and they have the resources, and I can expand my use of the resource or subtract. Good, right? Of course, open source has really come a long way, and that's got lots of manifestations. Going forward, anytime there's a hardware discontinuity, things happen and there's turmoil. Some of them are pretty predictable. I mean, you know, Moore's Law was great for a long time, right? I think it maybe still gets a couple more turns, but boy, it's sure getting pretty hard. Clearly, the clock rate stalled a while ago, which is why we got all these multi-core things and parallelism stuff. Power and heat are sure a lot more important. We used to really not care that much. Okay, CMOS guys used to laugh at the bipolar guys. Ah, water cooling. Well, you know, you look at some of those NVIDIA-based workstations with you know, water cooling. Well, okay, right. Disks keep getting more bits per square inch, but the bandwidth is more like a square root, and the seek rotation times are what they are, right? Okay, so sometimes there's predictable things, but the effects can surprise you. I think, you know, Internet of Things or wireless sensor networks is something we're going to see a lot more of, right? And there's already plenty of it around, and I'm not sure of all the implications of those. Chris Piester did dust networks and invented the term smart dust. I got him on a panel one time, and then another time he was on a panel, and I asked him, so you guys have talked about all these wireless sensor nets and how good your security is. So, like, what are going to be the moral equivalents of spam and viruses? And he says, oh, well, we've worked on this and this and this. But yes, someday your fridge will sell Viagra to your microwave. Okay, right? Yeah, okay, what can I say, right? Personal graphics, people know Werner Vinge, okay, right? A good science fiction author who's a network computing professor. Rainbow's End is like, imagine Google Glass, you know, but everybody's got contact lenses, and people fight over what reality really is, sort of the way Wikipedia edit wars work, okay, right? Where teams know what is the truth and they wish to impose their view of reality on everybody else, okay? Anyway, good book. It won a Hugo that award. You know, flash memory is more than SSD. You know, that's a lot of potential there, but there's a lot of impediments, like 4K byte pages, you know, are really ancient history from 360s and x86s. And these are pretty painful. You know, you talk to guys who build want to use flash memory for more usefully. It's a lot of work to do all the right stuff to make that work. It's just painful. It's also very rough on memory management units. Yes?
Apple has placed their flash on the PCI bus
Yes.
to head in this direction.
Yes, well, people
Put all kinds of stuff in, right? You know, all I'm saying is, it's sad but true. Okay, in 1989, I demanded that the R4000 be able to have a good range of page sizes, okay, right, with a decent hardware structure for it, because there was no way in the world you could build a memory management unit, a TLB, big enough for the size of memories that were coming, okay, right? You just couldn't, right? Not with 4K pages, right? And this is just a continuing problem, but again, it shows up worse when you have things like that, where you want to do something with 128K pages as a chunk, like a lot of flash.
R4000 was that
No. This is 64-bit microprocessor, CMOS.
Oh, okay. Who made this?
MIPS.
Oh, okay, all right. I didn't know that.
Yeah.
But you know, I did the sort of specifications for stuff like that. Okay, right? And I just said, look, we have got to do. We cannot build a big enough TLB on the chip when we just have 4K pages. But it took 5 or 6 years before the software caught up with it. It's hard work. Right? And unfortunately, a lot of things are pretty well stuck with 4K pages. Sometimes because it's in the software, like Linux has really got it.
Big Zero pages just arrived in Linux last year.
Yes.
A long time. Okay, open source. That's pretty important. This is another one where, like big data, you know, there's all these people running around like, big data, really? It's the newest thing. We've never heard of it before. No, I don't think so, right? Open source, it's the newest thing. It just arrived. I don't think so. I usually say, in some sense, it started back with David Wheeler when he invented subroutines for the EDSAC, right? In some sense. But certainly by 52, when John von Neumann gave away the plans for his IAS machine to anybody who came by, because, of course, you couldn't buy a computer at this point. You had to build it. So, you know, open source, okay? Hardware and software. IBM Share Users Group, right? That was the technical users group for IBM, and people shared stuff all the time, back and forth, right? DECUS got going. And of course, one of the ego things was to write software and get it on the DECUS tape, where they got put out and people, you know, I mean, it was programmer ego and reputation, right? You know, there was this weird hybrid thing called IBM Hasp, okay? Remember? Yeah, you remember that, okay. So this was, the IBM internal spooling programs weren't very good at that point. Hasp was written at Houston. It's Houston Automatic Spooling Priority System by IBM guys, but it got really liked by universities and research places. And there was this strange hybrid thing where IBM would give out the source to this, and they would actually take back changes that we made out in other places. And the assistant director of my computer center was Chuck Forney, and they actually, we'd get together at share meetings and sing songs like to Old Lang Syne, should old Chuck Forney be forgot, you know, okay. But it was very strange because it was this weird mix of proprietary IBM stuff and honest to goodness open source with lots of contributions coming from computer centers all over the place, right? And that was going on in the late 60s, right? Okay, inside Bell Labs, Unix was open source to all intents and purposes, right? I mean, you know, when I started, a release was that you drove up to Murray Hill and got on Ken Thompson's machine and saw what was there and made a copy, right? I mean, that was a release, right? Okay. Okay, now then, you know, we got it licensed out to universities on an as-is, don't call us basis. Now, the lawyers were not very keen about this, okay, right? Because we had a consent decree that said you shall not be in the computer business, and it was viewed as a concern if we got too close, right? Now, Ken Thompson and everybody involved thought it was really a good idea to get this out, okay, right? And I'm not sure how this happened, but he had a friend who was at a hospital who finally told the lawyers, if you don't give us Unix, you're going to see headlines in the New York Times, people die because of lack of Unix. And that was not true, but it was enough, I think, to push them over the edge. So, of course, this was a very clever ploy because it ended up that Unix sort of took over in the universities. We started getting to be able to recruit people who already were pretty proficient in it, okay, right? And it ended up, of course, wiping out a lot of the proprietary operating systems in the mini computer and other spaces. Then there was this one, John Lyons. Anybody remember that's the commentary on Unix? He took the edition 6 research code, put it in one book, and then did a line-by-line commentary. Which was widely used in a bootleg fashion by lots of universities because the AT&T lawyers did not like this, at the same time as we bought bunches of copies for use inside Bell Labs for internal courses, which was pretty funny. Okay, Ken was out here at Berkeley, right, in the late 70s, which sort of contributed to the 4.2 BSD stuff, right? Let's see, around about here there was the software tools stuff, which tried to get the Unix software into a more portable fashion, and it was a software tools Unix users group that shared things around, right? Of course, Unix V7 came out, and this was the point where we had decided that we had to make Unix portable not across different machines. We had tried to move Unixy environments onto IBM MVS and UNIVAC 1100s and all kinds of other stuff. And it was possible, but it was agonizing. So I said, look, we'll make Unix itself pretty portable. Well, that was pretty bizarre then. You know, I mean, that was just not something you did, right? A lot of people were like, what? Portable operating system of this size? What are you talking about, right? But it was the right thing.
At this time, Bill Joy is at Berkeley, basically with competing fork.
Okay, well, this is what's complicated, okay, right? It was sort of a competing fork, sort of because of AT&T lawyers. I told you, Ken Thompson was out there working with them, okay? We often ran Berkeley Unix inside Bell Labs because we preferred it over the version we got from the internal support group sometimes, okay, right? I mean, so you got to watch out. There's sort of competing forks, but you'd be surprised about how many genes went back and forth.
I remember Andy Bechtolsheim debating which OS
Yeah, sure.
at about this time.
Yeah, I mean, see, the thing is, there was a period here where in the 77 or so, Bell Labs management woke up to interesting pair of facts. The first was, by then, almost every project run Bell Labs depended on Unix in some way or other, and no two versions were alike. And this was viewed as a problem, okay, right? And so there was a consolidation tried to go on, right? Well, inherently, look, you know, Ken and Dennis and company, if they felt like changing something, they would change something. They were doing research. You could move pretty fast. And Berkeley Unix was sort of like that too, okay, right? You know, there was always the question, how could God create the world in 7 days? Answer, no installed base. And, you know, so things slowed down, and some of us, for sometimes, would say, oh, well, we may end up deploying on Unix System 3 or something, because that's the standard thing and stable and everything. But for some of our internal development, we'll use Berkeley something or other because it's got better network support. Okay? I mean, so the thing is, people like to portray this as a big war, but there was a lot of stuff going back and forth. You know, if you see the diagrams of different versions of Unix, it looks like a bunch of mating octopi, you know, right? Okay. Free Software Foundation came along, of course, GNU-C and Unix commands and stuff. That was good stuff. And then later, you know, Linux and others, you know, tried to redo it from scratch. But things like Apache came up, right, which were a great example of people getting together to build something that they needed, where it was a better idea to do that than to try to make some proprietary thing. Pardon?
Where was Minix?
Well, that was one of the ones that people tried, but it turned out Linux did better, you know, for whatever combination of reasons. I mean, there were a bunch of people who re-implemented Unix in some form or other, and this is the one that happened to catch fire. Yes?
A little institution at MIT was incapable of writing a competent kernel, so Linus did it for them.
Yes. Okay, well, you never know, right? Anyway, what I observe is,
gee, you know, open source, exactly where it fits and how has changed over the years, but there's been a regular progression from what's local libraries to one machine, right, through mag tapes we'd ship out in the 1970s to UUCP, the internet, web, GitHub, and everything. Basically, it's opened up what sharing there can be to lots more people, and that can be good or bad, right? I mean, it's good because you can share stuff. It can be bad because you can pick up, say, kind of insecure software and embed it in things worth billions of dollars, okay, which we've just seen, right? Okay, what, you know, Heartbleed. Well, okay, so it means, you know, it's a different world. It's not the old classic proprietary. If it breaks, I know I will call IBM and they will fix it, okay? It's different.
You'll call on it, yeah. Whether they'll fix it or not.
Well, I know, but you know, back when I was doing mainframe stuff, it might take them a while, but you knew who to call. It was theirs, okay? It wasn't.
yeah, they would at least answer the phone, okay, right?
And then again, so there's been this whole big.
An open source company.
I know, it's okay. So where did this go?
Well, Stack wars. I think we're in for another period of turmoil in the software stack here. And we got lots of different stacks fighting over who's going to do big data and distributed systems and things, right? And it used to be the whole stack was an OS, a couple tools and a few libraries. I mean, back in the 60s, that's what it was, right? I just observe to people, if you're building software on top of one of these stacks, think hard about what might happen, right? Like I used to say in the 1980s of microprocessor choice, it was like a funny kind of Russian roulette. Pick which microprocessor you're going to bet millions of dollars on, spin the cylinder, pull, and wait 2 years to see if you've killed yourself, okay, right? And I think some of that's like that now, right? So, as usual, best technology does not always win. Sometimes it's a combination of alliances and who else you get. Customers always help. And then the last thing where I'll end up, well, we'll have a few time for questions, is I observed in this business, anything that gets a substantial market lasts a really long time. Longer than you'd ever expect. And so now I will go forward to 5,000 years from now. That's from this paper. Where they asked me to write about longevity of scripting languages since I started shell scripting. And I said, no, this is a more general problem. So here was Werner Vinge from Deepness in the Sky. The hero is joined a starship crew, and he's learning to be a programmer archaeologist. That is, somebody who can dig down through the layer upon layer of software and fix things without breaking something the starship depends on. Because they've got trillions of lines of code, okay, that things depend on, right? Okay. So what's he do? He comes back, he says, the programs were crap. Programming went back to the beginning of time. Hey, stuff written 5,000 years ago before they left old Earth, these things still worked. At the bottom was a counter, second by second. They counted from the time about when the humans first set on old Earth's moon, but actually it's about 15 million seconds off, okay, right? The 0 second of one of the early operating systems. I recognize January 1st, 1970, aha, okay. Werner didn't say that, it's sort of an in-joke, okay, right? He says we should rewrite it. It's been done, it's been tried. You and 1,000 friends could work for a century or so, and it still wouldn't be upward compatible, right? And stuff would break. Don't mess with it. This is a mature programming environment, okay? And what I observe is, the stacks that people are using to build stuff now have gotten, deeper and wider. There's a lot of pieces there, right? And if you're going to be cost effective to build stuff, you got to use them, but you ought to think hard about what stuff you're building on top of, okay? So all I expect is over the next few years, we're going to see a lot of churning around in what are big data problems for one different kind of reason after another. But I've seen this kind of period of turmoil before, and I think we're only just getting going on it. So that's the end of the talk, and if you've got any more questions, I'll happily answer them. It's generally okay. I fought long fights in the 70s to get people to reuse code rather than writing it. Okay, right? And Doug McElroy started with that in 1968 at the NATO conferences. Okay, we need modules with good characteristics and being able to find them and put them together and not write code from scratch every time in every language, right? So I think it's good news that there's a lot more there. It's good news that you can go pick up a lot of stuff. It's different. And you've got to be careful, and you've got to think about whether or not there are good options in case something falls apart. So you have to put your effort in different places. I mean, I'm sure some of you folks grew up when I did when, you had a compiler, you had a couple little libraries, and you mostly wrote code. Well, these days there's an awful lot of stuff underneath. So, but mostly it's good because you couldn't possibly build the things that people build now unless you were doing it this way. It's just impossible, right? So, yes.
Some of us are thinking that these multi-core chips are going to make it a lot easier to write operating systems. What do you think?
No. No. Well, yeah,
okay.
Okay. Concurrent programming is hard. Okay, but look, for the operating system piece of it,
I think most of that class of problem is in pretty good shape. And the reason is, after all, people were building symmetric multiprocessor systems in the 80s on microprocessors. Yeah. So I said microprocessors. Oh. Okay. Gotta listen carefully. Yeah.
Control data, for instance, and peripheral processors.
Yeah, that's a little different. That's a little different. What I mean, though, is that certainly by the 80s, with people like Pyramid and Sequent and SGI and Sun, okay, there were a bunch of folks who went through what you had to do to take a sort of uniprocessor OS and do the right stuff to make it okay for multiprocessor stuff. So the first part was, at least if you were running independent tasks, the OS scheduling got better, lock management got better. It took a while, but I would say for a lot of applications, the OSs got pretty good, certainly by the late 80s, in dealing with multiprocessors. And the fact that multiprocessor happens to be multi-cores on that same chip, who cares, okay, right? Even in the 90s, we learned how to deal with memory hierarchies like the CC NUMA machines, where the access patterns are not the same. We got to know better how to deal with cache memory hierarchies, so that got better. Now, what's still really tough is doing applications that actually use the multiple CPUs. Because in the 80s, what we were doing was taking classic technical apps where sometimes you could vectorize or vector parallelize them pretty easy, okay, right? And they were in Fortran, and they were happy as clams to get, a factor of 3 performance on a 4 CPU system, okay, right? But taking arbitrary applications and making that work very well is still hard. So so there's more compute power there. It means if you've got multiple concurrent things, you have less worry about having to do time sharing between them because you've got more cores, okay? So that part helps. But if you really want to get full out performance, it's hard work. It's also very tricky. If you look at the current chips, they do stuff like raising and lowering the clock rates. They turn cores off so that they don't melt. There's all this horrible stuff, okay? So.
They have a lot better shared memory, though.
Well, they have a lot of shared memory. We had as good as shared memory in some sense between in the symmetric multiprocessors. It was equal access from anywhere. Okay.
It was equal, but it was very slow.
Well, sure it was.
We're off chip.
Sure, it's still slow when it's off chip.
Now you can put a lot more on a chip.
Sure. It's always the same. If you can get it right there next to the CPU, life is good. And then you drop off the cliff, okay?
It took Sun's effort to re-engineer the network interface to be multiprocessor aware so that the locking processes of coming into the I/O no longer slowed down network traffic.
That's right. Networking is really ugly and bad, okay, right?
The hardware was re-engineered after they saw the needs from the software.
Yeah. Oh, yeah. Well, I went through the SGI, too. Greg Chesson over there, okay, right, did a huge amount of work in high-performance networking, and I used to spend a lot of time trying to figure out what CPU features we could do to sort of help them out, okay? The thing is, the classic microprocessor models, networking I/O is just ugly compared with, hey, I want to do a disk I/O, I scheduled it, it comes, it's a nice size, it doesn't surprise me, it doesn't just appear out of nowhere and suddenly demand attention. It doesn't have weird buffer sizes and things.
Right. It's the data you asked for going where you told it to.
Right. Yeah. So anyway, look, multi-core, it isn't a question whether it's good or bad. It's here. It will stay. It's extremely difficult with any of the obvious technology paths to get the clock rates to really go up a lot, okay, right? We got that for free for a lot of decades, right? It's not there anymore, so what you get is multi-core. Now, where it really is wonderful, of course, is in the graphics turf. Okay, right, where there's a huge amount of inherent parallelism, all right? And of course, that's backed up now. Folks like NVIDIA sell a lot of chips for supercomputing applications because with the right apps, you can get a lot better compute power per watt, okay, right? And that matters, right? So you'll find big supercomputers that'll have an x86 with one or more graphics chips hooked to them, just because they give floating point computation rates that are hard to beat for the right problems. They're not necessarily the easiest things to program. Yeah. Any other questions?
On the other end, what about small things like the Raspberry Pi and the internet of tiny things?
Okay, well, that's a whole different topic, but yeah, I think the issue with whether it's Raspberry Pi or the sensor networks or the fridges that are smart or whatever is there's a whole lot of extra data sources that are coming. Right. Fortunately, most of those data sources are fairly low bandwidth. But you start to look at things like the sensor-based stuff, all the personal medical monitoring and things, okay, right? There's just all these data sources that get added in, and they're big data. They're not so much, like a 15 terabyte oil and gas data set. But there's a huge number of sources and a lot of stuff you want to keep, and you got to manage, and it's complicated and messy and all that stuff, right? So, I mean, I think that's one more source of stress, and I think I even mentioned that in the 1998 talk. It's just, there's a lot more sensors out there that can generate stuff you care about, so. And, Raspberry Pis are cool little things, and they may generate more data yet, But fortunately, the little things that tend to have low power requirements, they can't send that much data or they die quick.
Yeah, it's interesting. I was visiting a friend in the hospital the other day, and there was this machine over there monitoring his heart.
Yes.
How long do they keep that data?
I don't know.
Don't ask, don't tell.
It's not that big. You might as well keep it.
Yeah,
Yes.
a long time. Yeah.
Cost
But on the
more
other
to
hand,
delete it.
if you look at things like CAT scans and MRIs and stuff, data adds up pretty fast. Just heartbeat stuff's. Pardon?
Volume data.
Yeah, volume data. Yeah, volume data. Ooh, big stuff.
Yeah, but they're expensive, so the cost of keeping the data is.
Yeah, I know, but they generate a lot of data, and you got to worry about it. And I mean,
keeping it, it's the cost of processing it.
Yeah, but the graphics chips and stuff have helped with that a bunch, okay, right? But you got to manage it, and remember, the medical guys have to live under some really stringent rules, okay, right? That some of the rest of us can just sort of ignore. I mean, they've got lots of privacy issues and control on that stuff, and how long they got to. I mean, sometimes people get irked at the medical folks for being really slow on technology. They've got some challenges.
On that one, I'm with Palo Alto Medical, whatever. When they switched over to computerized, suddenly all the doctors said, when they asked about privacy, who owns the data? Oh, that's the company the hardware. What do you mean by that? I mean, yes, that's de facto happened. So yes, we lost all the privacy.
Yeah,
the lawyers were too late.
Yeah. Well,
they had no clue or whatever. Yeah. Although the guy there in Panfis, CS type, knows what he's doing, but somehow I guess they never talked to the lawyers.
Yeah.
All the people that never software, hardware, they only hijacked it. Period. Forget about it.
Well,
it's gone.
They've got challenges. Okay. Fortunately, the younger ones are a little more hip on this stuff. The older ones didn't want those computers in there in the first place.
Yeah.
So can you comment on the romance between the refrigerator and the microwave? Earlier you mentioned the selling.
It wasn't romance, it was selling Viagra, okay?
Well, I want to know that my microwave will still get hot in the kind of way.
But the right way. Huh?
Yeah. Well, I think the general. I mean, obviously that was humor, but there was the general thing of, okay, so you make smart houses with every appliance being smart, and they talk to each other, and they adjust how much electricity they're using, and gee, maybe the PG&E tells the fridge, hey, if you can turn down here for an hour because the power's tight right now, blah blah. Okay, right. And now the question is to what extent do these things communicate? Because of course, if you do wireless mesh networks, you want things to talk to each other so they don't have to send messages too far. And can they get in each other's road, right? And
groceries. And
that's right. I worried about that is that if the fridge can order groceries, the fridge can call my doctor up and say, there's a piece of chocolate cake here. He shouldn't have that, so okay, all right, Yeah, there used to be a piece of chocolate cake here. And there's a chocolate cream pie too. This is bad. Okay.
Keep you in line? Is that
that's the worry. Yeah, right. Yeah. So, I mean, it's pretty clear. I mean, look at the Nest devices. Nest devices are getting pretty smart, right? Okay. And certainly, I've always wished for, how many things in your house think they know what the date and time are, or at least the time? And how good are they when daylight savings time changes of changing themselves? The answer is there's a whole lot of things that think they know what time it is, and they're mostly wrong. All right? All right? Well, pardon?
More or less.
More or less, yes. Never within an hour, that's fine, right? Well, okay, maybe we'll have something that, figures out from the network what time it really is here, and does the right thing. Now, part of this, one of the cool things in this book is that most of the computing at this point is done by dust mote-sized things that are floating around, have sensors and effectors and things, okay, right? And the hero, way back, managed to get his own trap doors in the software, okay, right? And he can get clouds of these things to recognize him, and he takes over some things, okay, right, And the software is so complicated in these dust mote things that the bad guys haven't been able to get deep enough in there to figure out what's going on, okay, right? So, it's
Not as good at hackers as the good guys?
in this case, the good guy got there a long time before, and what turned out, he said he always thought that if you could get a trapdoor in something that became a pervasive standard technology, you could rule.
Primary virtual machine.
Yes, right. That's right, yes. Carl.
Is the NSA data center outside of Salt Lake City the world's largest data center for big data? Is it the biggest of the big?
It's one of many.
Let's see. I don't know, but if I did, I'd probably have to shoot you before I could tell you.
It's one of many, and they don't shoot you.
Yes, but at one point, I did calculate that people know the top 500 list of supercomputers on, LinPack, basically, okay, right? On a raw gigaflops or teraflops rate, whatever it was, I calculated that the most compute power in the United States on that was a warehouse in Seattle that had 500,000 Nintendo N64 games. Okay, right? Now it had a little I/O problem because finding 500,000 kids, to talk to each other was not probably good. But there's I have no idea if the NSA Center is the biggest one compared to some of the other ones that Google and company have out there, but it's clearly pretty big.
Why does it need to be so big? You calculate all the video, all the text. The voice is nothing.
Voice is nothing.
But, okay, calculate all the video that they
Yes.
could possibly be capturing, right? And it seems like that their data center is too big. They can store it.
Anybody can comment.
Okay.
Put a comment.
Okay, so you should know, all right? I mean, I don't know how many people have dealt with the NSA, CIA, Defense Signals Directorate, but I used to. Okay, right? Okay, and there's a rule about disk space. Disks are either new or full. Right, okay, all right. And in some sense, that similar thing applies to somebody like the NSA, is that if there's data to be had somewhere, they'll figure out a reason to want to have it. Okay, right, and you never want to run out of space, so you plan big. I mean, okay. So I don't know. I haven't. It's been years since I've had any embroilment with that. I mean, well, okay. I tell a story here. So Ken Thompson did a Turing Award lecture, right, in the 70s or 80s, I guess. And this was about one of the first worm programs. Okay, right. I don't know if people have ever read John Brunner's book Shockwave Rider. Okay, right, which is a dystopian future where the hero has a worm with an infinitely replicating tail that will seek out all mentions of him in any database and change things so that his identity becomes invisible to people. It's very cool, right? And I read this book around 74, 75, and I laughed. I went, cool story, but and within a week I'd seen one. Okay, all right. We were the only ones to ever find it, as far as I know, is that Thompson put a thing in the C preprocessor where if it ever saw the Unix login program, it looked for a line that said, if encrypted password matches, then okay, and it added, or if magic password. So if you ever recompiled login with this thing, you would now have a giant trapdoor in your system. Okay, right? And it wasn't, okay, so that was the first thing. The second thing is it looked for itself and it reinserted this code, okay, right? But this is back when the software C was getting bootstrapped so fast by Ritchie that he would add new features to the language, and then he would recode the compiler to use those features. So you got the new source and the binary that went with it. The binary could compile the source, but your old C compiler could not compile the new source. Okay, right? So you kind of have them both, right? So you never saw this gimmickry in the source code. Okay, right? Well, one of our guys noticed there was a function name in a binary that didn't appear anywhere in the source, okay? And I went and looked on Ken's machine and found this, okay, right? But I don't think anybody else did. And they were exploring different password schemes, what the implications were, how much could you trust the people you got software from? The answer was, you better think hard about who you get your software from, okay, right? And the funny thing was, and the reason I wouldn't answer this question about the NSA even if I knew, was I was up in the terminal room, probably talking to Kernahan or Ritchie or somebody, and Ken and Bob Morris Sr., okay, Bob Morris Jr. is the one who did the internet worm, you know, right? At that point, Jr. was a high school kid who used to come by there, okay? Bob Morris Sr. sometimes consulted for the NSA, right? And he and Ken were sort of chortling away about this. Oh boy, this was really fun, you know, it really, really showed people you shouldn't trust people as much as they think, blah, blah, blah. Hey, you think we could put this over in the NSA? Because they were using Unix already. But, oh yeah, that'd be really fun, blah, blah, blah. And then I think it must have been Bob said, you know, they don't really have a sense of humor. So that's why I would never answer that question. I do, but they don't. Actually, some of them, Defense Signals Directorate is the NSA equivalent in Australia. Okay, I used to go there, right? One year I was there, and I just been pushing to get Linux product lines into SGI for parts of stuff that we couldn't address. And the DSD guys were hassling me that we couldn't ship them a machine directly with Linux installed. And that was an era because Linux had crypto code. Okay, it was munitions, and therefore we could not ship it out. So we had to ship the hardware there, and then the local office in Canberra would install the software. And the DSD guy, so what is this? Okay, and I said, well, you know, we have these rules in the United States where yes, this is open source software on a Finnish website that we got, but we cannot ship it to you, especially, you know, Australia. Well, I don't know about you guys, and you guys at DSD, well, you could be dangerous. Well, they had a good laugh, I had a good laugh, because I knew, and they knew I knew, that they trade code with the NSA all the time. Well, we couldn't ship them Linux, you know. Okay, so I think we're about done. So, one more question.
Yeah, obviously, big data, you'd think, would be stressing people's ability to write software. And what do you see on the horizon as far as maybe languages for...
Well, I mean, I think it does in one sense. I mean, sometimes it's, you know, there are things that are complicated software, but then there are things where the difficulty is simply there's a lot of data to plow through. Okay, right? People are doing all kinds of different data exploration tools and things at this point. This is why I say there's a lot of turmoil, because lots of people are having to do things to cover the scale that they're doing, right? So I don't know I can't say this is the answer, but clearly people, you know that they need better tools for this stuff, and people are doing it. And you know, I think better things will come out.